This is number 11. That's where part 2 starts. I want to take the derivative. This is all to do with derivatives and integration of exponentials. So when x and y are mixed together, this is going to be done implicitly, and be aware when it's the product rule. So y times e to the x is a product rule. So the first times the derivative of the second. The derivative of e to the x is e to the x. It's the best rule ever, and it's the new rule. Plus the second times the derivative of the first. Now, the derivative of y is 1, but it needs a hook on y prime whenever you take the derivative with y in it. Keep going. X times e to the y is also the product rule. That's the first times the derivative of the second. So the derivative of e to the y is e to the y. The derivative of the exponent gives you the hook on y prime, plus the second times the derivative of the first. Well, times 1 keeps it as e to the y. And then the derivative of 10x is 10. So that's the hardest step and the first step. Now, the rest is algebra. So e to the x y prime and x times e to the y y prime. So these two terms, they're going to stay. Everything else is going to be moving to the other side. So we have a 10. We're going to subtract y e to the x, and we're going to subtract e to the y. So that we have rearranged this, so only the y primes are on one side of the equation. Factor out a y prime, and you have e to the x plus x times e to the y. Divide. And you have your answer. So that's implicit differentiation. Let's try number 12. In number 12, it's similar. It's implicit. E to the exponent xy subtract x squared equals 0. So I want to know, can you follow some derivative rules and take the derivative? Honestly, you just have to be a good rule follower to understand how to do these rules. So I want to take the derivative of this, e to the xy. The derivative is e to the xy times the derivative of the exponent gives me the hook on. So the derivative of the exponent is a product rule. That's the first times the derivative of the second plus the second times the derivative of the first, which is 1. So times 1, it's just y. And then negative x squared, the derivative is negative 2x, and the derivative of 0 is 0. Now, I'm going to distribute. So we have e to the xy times xy prime. We have e to the xy times y. And now I can get y prime by itself. So e to the xy, xy prime is going to stay. Everything else is going to move. So we're going to add 2x and subtract e to the xy times y. And then the last step is to divide. Now there's also an x here that we're going to divide out. So really it's x times e to the xy. That's what gets divided. And there's your answer. As always, I double check to make sure answer key that I wasn't just fooling you. So for number 12, there's the answer. All right, not fooling you yet. Number 13. Number 13, write an equation for the line tangent. So right away I'm going to write down x equals y equals and the slope. And so the point is when x equals 1. So to find the y coordinate, I plug in 1 for x. So e to the exponent 1 squared minus 4 times 1 plus 3. And then the slope is the derivative of that, which is e to the exponent x squared subtract 4x plus 3, and then the hook on is the derivative of the exponent. So let me show you my work now. So x is 1. Plug in 1 for x to find the y value. So if I simplify this, it's 4 take away 4, which is 0. So e to the 0 equals 1. Here, I'm going to again plug in positive 1. Well, we just said that if I plug positive 1 in, this becomes 1. So if I plug positive 1 in here, 2 take away 4. If I simplify it, that's 1 times negative 2, which is negative 2. Oops, let me put this negative 2 up here. And now the equation would be negative 2, x subtract 1 plus 1. All right, number 14. Says, find the domain of y equals x times e to the x, subtract e to the x, intercepts extreme points of inflection, and then sketch it without a calculator. Here we go. So let's just break this down. The first thing I notice is that I can factor out an e to the x, and that gives me x subtract 1. So when I make it equal to 0, e to the x can never equal 0. So there's no solution there. But x subtract 1, that can equal 0. So right away, I know when x equals 1, there's an x-intercept. That's a 0. So an x-intercept is at 1, 0, and it's odd, which means it's going to cross over. It has an odd exponent. The y-intercept, you plug in 0 for x. So e to the 0 is 1. 0 subtract 1 is negative 1. So 1 times negative 1, the y-intercept's at negative 1. So we already have 2 points for our graph. Are there any restrictions for an exponential? No, positive, negative, or 0. So the domain is all real numbers. There's no holes or breaks or jumps or asymptotes. The range, they have to even ask for the range. So now we're going to take the derivative. This is going to help find the extreme values. That would be the maximum and the minimum. So x times e to the x. Or we can do this one here on the right. Both are going to, I think this will be actually faster to do. So let's do the one on the right here. They're the same. Do the product rule. That's the first times the derivative of the second, which is 1, plus the second times the derivative of the first. And the nice thing about e to the x, the derivative is e to the x. Again, I'm going to factor out an e to the x. Make it equal to 0. Now, again, e to the x can never be 0. So if you take each factor equal to 0, e to the x has no solution. But this one does. If I go 1, take away 1, this is really e to the x times x. And as such, if you make it equal to 0, the only solution there is at 0. So when x equals 0, all of this is 0. So I'm going to draw a number line, and 0 is the only one I'm going to look at. Now, into the derivative, if you plug in a negative number, e to whatever will never be a negative answer. E to whatever the exponent is will always be positive. So if you plug in a negative number for x or a positive number for x, you can see at 0 is going to be a minimum. So a 0, negative 1 is a minimum. No maximum. Let's continue over here. The second derivative will go from here. Again, the product rule. First times the derivative of the second times the derivative of the first. And again, make it equal to 0. Factor out an e to the x. And then solve this. So e to the x can never be 0, but here you can tell one of the solutions that would make this 0 is negative 1. So we're going to draw a number line just for negative 1. And again, e to the x will never be negative, so it's always a positive number. So if I plug in a number smaller than -1, the answer is negative. If I plug in a number bigger than -1, it's positive. We have a point of inflection at -1. So if I plug in -1 into here, -1 take away 1 is -2 e to the x. And -2 e to the x, and x is -1. That's the point. Let me just write that down, like -2 e to the -1 is like that. So remember that e is about 2.7. So when you divide this, it's a little bit smaller than -1. We can only estimate it on a graph. All right, let's just summarize what we have so far. I want to put the point 1, 0, 0, -1, and -1. And if I would approximate a -2 over e, that's like -2 over e is like about negative point, I don't know, it's less than 1. So like -0.8 or something like that. So we have 1, 0, 0, -1. That's a minimum. And then at -1 and like -0.8, so like somewhere like there, that's going to be a point of inflection. So now let's follow the number lines. So I know, first of all, it's decreasing and then increasing. And it's concave down to begin with. So it's decreasing, concave down. After -1, it's concave up. And we have a graph of it. Oh, and you know what? I made a little mistake. Do I have a whiteout? I don't, do I? So do you know what mistake I made? It's okay. There's only one x-intercept. So it doesn't just cross over because you want to cross over this. So it is decreasing, but the left end behavior actually is getting closer to 0. So on the left end, it does not cross the x-axis. We only have one x-intercept at 1. So it is decreasing, and it's getting closer to 0, but it's not going to cross. So there's like a little asymptote. So the left end behavior there, you can see. So as you put in large negative numbers, the answer is going to get closer and closer to 0. And then on the right side, you can see the behavior. All right, there's the sketch. Number 15. All right, so now is practicing integration. And again, the good news with integration is the integration of e to the x is e to the x. So it's super simple. If the base is not e, it needs an extra anti-hook-on of dividing by ln of whatever the base is. So let's see if we can figure that out together. So this is called a definite integral. So we are going to substitute in the upper and lower bound at the end. So step 1 is the hook on here is 3. So that's what I'm going to put in. And I'm going to undo it in front, and then I'm going to undo the hook. So the rule to this is we have 1/3 times 2 to the 3 over t, and then you divide by ln 3, the base. So the rule again is you copy it down, and then you divide by the ln of the base if the base is not e. If the base was e, you wouldn't have to divide by that. So if I put this together, you can put 1/3 and ln 2 together. And then we plug in the upper bound and then plug in the lower bound, and you have your answer. You could also write the answer like this. So you could write down 1 over 3 ln 2 in front, and then plug in the upper bound, lower bound. You could also, I don't feel like simplifying 2 to the 12, so that's a great answer right there. Number 16. Let me double check, make sure I'm not fooling you. That's a great answer. Of course, sometimes I make mistakes, but then if I do, I tell you why I made it and what I did wrong. I don't pretend I didn't make a mistake. Negative 1 to 1, e to the exponent 1 subtract 2x dx. So again, this is what's called a definite integral. So I know at the end I'm going to plug in the upper and lower bound. The base is e, so that affects the rule. So the first thing I'm going to do is make sure I know the hook-on factor, and then unhook it. So the hook-on for 1 subtract 2x is negative 2. And then to undo that negative 2, it's negative a half. Now, once it's set up, you can unhook this, and then your answer is going to start with negative a half, and then you just copy it. E to the exponent 1 subtract 2x. And that's the great rule of e to whatever the exponent is. The rule for the integration is copy. That's it. And you just had negative a half is what needs to be a part of it. If this base was not e, then you'd have to divide by ln of whatever the base is. And now substitute in. So first we're going to substitute in 1. And then we're going to substitute in negative 1. I don't need to simplify it. It's done. Number 17. We're integrating from 0 to 2. E to the x over 2 subtract x dx. Just trying to set this up in a way that makes sense. So for each one you can integrate separately and then bring it back together again. So if I look at e to the x over 2, the hook on is 1/2. Well, to unhook 1/2, what number do you need in front? And so that number would be positive 2. So the hook on is 1/2. To undo 1/2 times 2 undoes it. So we need 2, and then the rule is just copy it. For x, it's just x squared divided by 2. And then we're integrating from 0 to 2. Plug in the upper bound. Subtract, plug in the lower bound. Never assume the lower bound, if it's 0, that the answer is 0, because this does not simplify to 0. But that's a good answer. Number 18. By the way, if you did want to simplify this, it's not that big of a deal. E to the 1, so this would be 2e. 2 squared divided by 2 is 4 divided by 2, which is minus 2. This part is 0, but this is not. E to the 0 is 1, so you minus 2. So altogether, that's 2e subtract 4. So that isn't a big deal on multiple choice to get there without a calculator, if you had to. Number 18. Number 18 is the integration. Now this one is an indefinite integral. E to the 2 over u divided by u squared du. Let's rewrite this so it makes better sense. So u squared can be written as u to the negative 2, 2 over u, can be written as 2u to the negative 1. So notice how I write it with no fractions, and I use negative exponents. Next, I'm going to focus on e to the exponent 2u to the negative 1. The hook on for this would be negative 1 times 2, so the derivative of the exponent would be negative 2 u to the negative 2. Subtract 1 to the exponent. And now compare. They both have the same term, but I need to undo the negative 2. So I put down negative a half in front. Now I can circle the hook and unhook it. So I start with negative a half, and the rule for e is you copy it. And then don't forget the constant, because it's an indefinite integral. Number 19. I just keep looking over and make sure I did it right. In number 19, you're integrating 2x subtract 1 times 10 to the exponent x squared subtract x dx. So you have to have a sense of what's u and what's the hook on. So the primary is the exponential, and then I rewrite this and I go, what is the derivative of the exponent? What should be the hook on? And that's 2x subtract 1. So it matches, which is awesome. Because they match, I unhook it, and then the rule. So the rule is you copy it. The base is not e, so we need to divide by ln of whatever the base is, which is 10, and then don't forget the constant. Number 20. Number 20, we're integrating e to the negative 3y, subtract 2, all to the exponent 5, and then e to the negative 3y dy. Okay. So recognize the primary compared to the hook on. So in this situation, we're looking at the derivative of the base that's going to create the hook on. So the derivative of this base is e to the negative 3y, and then the hook on for negative 3y is negative 3, so there's like a double hook. The derivative of negative 2 is 0, so I don't need it. And then I'm going to rewrite e to the negative 3y, subtract 2 to the 5 dy. So that's the correct hook on with this base. What I have is something similar, but I have an extra negative 3. So to undo it, I need a negative 1/3. Then I circle the entire hook. I unhook it. And then the answer is negative 1/3. The rule here, this is not an exponential rule. This is now the power rule. So we're going to add 1. So we write down the base, e to the negative 3y, subtract 2, add 1 to the exponent, divide, and then the constant. Number 21. The step 1 here for 21, I'm going to write it calculus friendly, so it's 2 subtract e to the negative x to the exponent negative 1/2. So you should have that skill by now. And then I write down the derivative of the base. So the derivative of 2 is 0, but the derivative of negative e to the negative x is negative e to the negative x. And then the hook on for negative x is negative 1. So this actually becomes a positive e to the x because of that hook on, negative 1. Next, I look and I realize that they match. So I unhook it, and then I add 1 to the exponent, and then the reciprocal, and don't forget the constant. 22. Integrate e to the bx squared, subtract a times x dx, where a and b are constants. So step 1 here is, in this situation, the hook on comes from the exponent. So I'm going to copy it down. The derivative of the exponent is 2b times x. Negative a is a constant, so the derivative of any constant is 0. So it's 2b x, subtract 1 from the exponent. Now look into, how do I undo it? I have x, 2bx. So to undo it, it's simply 1 over 2b. So when I multiply it out, they would be equivalent. Then you can circle the whole hook, unhook it, and then your answer starts with 1 over 2b. And then the rule for e is you just copy it. And don't forget the constant. Number 23. Hopefully more and more you make a choice of trying it first and then pressing play, but only you know what support you need. 23, I'm integrating e to the x, subtract e to the negative x, and then e to the x. Oh, why did I do that? I need to rewrite this. I'll show you. All right, let's integrate this. It's kind of a puzzle, right, to undo a bit. So I need to write this calculus friendly. So we have e to the x subtract e to the negative x, multiplying e to the x plus e to the negative x to the exponent negative 3. So we have no fraction. The hook on here comes from the base of this. So look at the more complicated algebra. The base of that is where the hook on is going to come from. So I'm going to write down what's the derivative of this. So it's e to the x, and then it's e to the negative x. But it has a hook on. The derivative of negative x is negative 1. So that's going to make this subtracting and not adding. What do you notice is they match exactly. That's so pretty. So you undo it. So you unhook, and then the rule is you add 1 to the exponent and divide. On to 24. And this is the last, right? No. Oh, I don't know. I don't know what I'm saying. So I notice for number 24, we have a monomial in the denominator. So that's an indicator. They're going to write it as 2 fractions. So one fraction is x times e to the 2x over e to the 2x. And the second one is e to the x over e to the 2x. So see how I write this as 2 fractions to simplify it so I can do the power rule? So I write it as 2. So e to the 2x divides out. Here, if the bases are the same, you subtract the exponent. So x subtract 2x is negative 1x. And now you're ready to integrate. So the antiderivative of x is x squared over 2. The antiderivative here would be just copy it. Now there's a hook on of negative 1. So that's actually going to make the negative, and the hook on negative makes this plus. And then you just copy it. And that's the rule. Done. There's 24. can you approximate that integration? And then first we're going to use a left-hand Riemann sum. And then we're going to use the trapezoidal rule where n equals 4. Sorry. And then the second one, I'm just going to write down the trap rule and with 4 again. Good review. So what's step 1 for these to integrate this? So if I'm using rectangles and it has a common width, that common width is found by going top subtract bottom divided by how many rectangles you have. So that's 1/2. So it's going to start with 1/2. And then a left hand, you plug in 0. And I'm not going to simplify it. Oops. So where there's an x, you plug in 0. Plus, that's the first height. That answer is 0. And then the next height, because we're going by halves, the next one will be 1/2. The next one will be 1. I don't need a 1 in front. I don't need a 1 in the exponent. It's a left-hand one. So left, 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 one more left. The last interval, you plug in 3/2, or 1.5. And that's called the left-hand Riemann sum. And if you need to visualize it from 0 to 2, here are 4 rectangles. And so the first one goes from 0 to 1/2. So you're using 0. Then 1/2 to 1, you're using 1/2. From 1 to 1.5, you're using 1. From 1.5 to 2, you're using 1.5 or 3/2. Just to be able to visualize it. Well, you do this too for the trapezoid. So there, right there was the Riemann sum. Now, how would that look different for a trapezoid? So the width is going to be the same. So they have a common width of 1/2. Now the formula for a trapezoid starts with 1/2, then the common width, and then we're going to use each one of these. So it's every 1/2. So we start with 0, and then we double the next height. We double the next height. We double the next height. And then it's the last height that we don't double. Now it says 2 only because we're plugging in 2 into here. So it's 2 times e to the 2. But that's not doubled at the end. So notice this is the formula for a trapezoid. The first and last are not doubled, but each other one is doubled in the middle. That's the trapezoidal rule. Number 26. Find the function whose derivative is negative 6x squared plus 2x plus 3, and whose graph contains the point 1, negative 4. So if I want to find the graph g at x, I need to integrate the derivative. If I integrate this, add 1 to the exponent and divide, add 1 to the exponent and divide, and then the antiderivative of 3 is 3x, and then the constant, and then we have a point to plug in. So we make it equal to negative 4 and plug in. Now negative 6 divided by 3, I am going to simplify it because we're in the middle of the question to make it easier. And now I'm solving for the constant. So I make it equal to negative 4, I plug 1 in for x, and now I solve it. So this is negative 2 plus 1 plus 3. This is 4, take away 2, subtract 2. So I get c is equal to negative 6, double check. Yep. And then if you put it all together, what does the function look like again? Remember back here? So it's negative 2x cubed plus 1x squared plus 3x minus 6. Remember, this comes from right here. And I simplified. And we found c is negative 6, and we put it all together. Number 27. A paintball is shot vertically from a position of 6 feet below ground level. So when t equals 0, so our position equation's there. S at t equals negative 16t squared plus the initial velocity. So v sub 0 is 128. And then S0 is the initial position. 6 feet below ground level would mean subtract 6. There's our position equation. At what time does the paintball reach its maximum height? So I'm going to take the derivative of that. Make it equal to 0. Take the derivative, make it equal to 0. Does 32 go into 128 evenly? Of course it does, 4 times. And that's in 4 seconds, let's assume. Yep. We should also really show derivative in a sentence. So into the derivative, if I plug in positive 1, you get a positive answer. If you plug in a number bigger than 4, like 5, you get a negative. So it shows that that's a maximum. In 4 seconds, the paintball will reach its maximum height. Done. Part B. What is the maximum height of the paintball? So we take that answer 4 and we plug it into the position function. So I'm just going to do the hard work for you, and that answer is 250 feet. So we take that answer 4, you plug it into the position, calculate it, done. Part C, what's the paintball's velocity at t equals 3? So that's into the derivative. And it's that 3 seconds. So plug 3 into the derivative. And you get 32 feet per second. Make sure the units are good. So again, plug 3 into the derivative of the position. That's velocity. Plug 3 in, and you get your answer, and it's feet per second. Part D. At what time does the paintball reach ground level? Make sure to express all that. Now, ground level means equal to 0. So we take the position equal to 0. This is a calculator question. It's not factorable. Can I just show you it on the calculator quick? So how would you solve this? Press menu. It's an algebra question. So go algebra, solve it, and then you type in negative 16t squared plus 128t, subtract 6 equals 0, comma t, and that's it. So at what time is it at ground level? So at the very, remember it starts below ground level, so it's at the ground level right at the beginning, right? Because it starts below the ground, so like you dug a big hole in the ground. So it right at the beginning, it's at ground level, 0.047. And at the end, it's at ground level at 7.952. and don't feel you have to round. So that's at the beginning of the journey. Remember, it starts in the ground. So as it's rising out of the ground, it's at ground level right at the beginning, and then that's at the end when it hits the ground again. Number 28. In number 28, sketch the region bounded by the square root of x plus the square root of y equals 4, x equals 0, y equals 0. Then set up the integral for the area of the region and use a calculator to find the area. All right, what would I do if I had to sketch this? So first of all, I know that all the values are going to be in the first quadrant because you can't have negative for x or negative for y, so that's a good start. 0 does not equal 4. So I'm going to find some points to like put into this that would then match this equation. So I know the square root of 16 is 4. So if x equals 16, then y equals 0, because the square root of 16 is 4, and the square root of 0 is 0, so it equals 4. So I know over here it's 16. And then if I flip it around, I could actually also do this if I flip it around, that the y-intercept, when x is 0, y must be 16, so that it simplifies also. That's just using some number sense. And then there's a curve. Now, is this concave? How would it be concave-wise? Is it going to be concave down or concave up when I do it? What's another point I could put maybe in the middle? So let's say that x is 1. I mean, I could also write it like this. I can write it as the square root of y is equal to 4 subtract the square root of root x. And then I could square both sides. And then I could plug in values that would give me an answer. So maybe that's the best. So if I plug in 1 for x, that's 4 take away 1, so 3 squared, so 1, 9. What's another one I could plug in? Well, I plugged in 4 already. I plugged in 1 already. I plugged in 0 already. This is what the curve's going to look like, right? Because this point, in terms of like it's not concave down, because of like where it's positioned, I can see it's concave up instead. Connect the points together. So we have a region, right, that we are doing. Now, what are we doing with that region? Set up an integral and then use a calculator to find it. So how do we find the area of what I just shaded in? So first of all, we'd integrate from 0 to 16. Oh, I could have found another point. What was the obvious one I didn't... I could, if I plugged in 4, right? I wasn't even thinking. If I plugged in 4, the square root of 4 is 2, and 4 take away 2 is 2 squared. So 4 4s on my graph too. I also could have plugged in 9. Square root of 9, that gives me 1. So you can see how it's decreasing. I could have found more points. 1, 9, 9, 1, 4, 4. Notice how every point is like an inverse that's already on the graph. Anyway, I'm integrating from 0 to 16. I wrote it this way. So if you write it this way, it's the x's. So it's top subtract bottom. So that's going to be 4 subtract root x squared dx. So the bottom is 0. And there's your setup. Use your calculator. We're integrating from 0 to 16. Parentheses. 4 subtract root x. Move the cursor. Square it. And that's dx. Oops. Actually has a nice little answer to it. So 42.666, or there you go, 667. Done. So you could have actually foiled this out and do the antiderivative, plug in 16, subtract 1, and you would have actually gotten a rational answer out of this. So you didn't have to use your calculator, but it was nice that you could use it. 29. Coming to an end here. In number 29, the solid, so set up integrals for computing the volumes of the solid described in problems in R is bounded by y equals ln x subtract 1, y equals 0, and x equals 4. So this is definitely a calculator question. It says set up but don't integrate. What that would look like. So first of all, I don't know, you probably don't remember logarithms. So why don't I just do a quick, there's a lesson coming up to remind you. Y equals ln x. This is what the graph looks like. It actually has an intercept here at 1. So ln 1 equals 0. And this is the curve of it. Now, if this has been shifted 1 to the right, then that same picture, instead of at 1, would now be at 2. And actually at 1 would be an asymptote. And there's the picture. We're integrating this y equals 0 and x equals 4. So that's 2, 3, 4. So this is the area right here. So we have y equals 0, x equals 4, and the curve, it's trapped by that area that I just shaded in. Let me remind myself what I'm doing again. Find it revolving about the x-axis. Just the setup. So on the x-axis, it's a disk. So the setup is a circle. So it's pi. So it's pi r squared, the circle. It's integrating from positive 2 to 4. And then the radius at any time, top subtract bottom, is the curve subtract 0. So just put in the curve ln x subtract 1, and you have the setup. That's for 29. 30, same thing. Let me redraw it again for 30. Now we're going to revolve it around y equals negative 2. So I redrew it, but now it's y equals negative 2. So if I do that, this is now going to be a washer. So we're still integrating from 2 to 4. We have a big radius. We have a big radius and a small radius. Now, for the big radius, go from the line of revolution through the area to the top of the area. And then just go top, subtract bottom. So the top is the curve, which is ln x minus 1. subtract the bottom. So when you subtract a negative, it's really adding 2. That's the big radius. The small radius is from the bottom, from the line of revolution to the bottom of the area. That is just 0, subtract negative 2, or just the radius of 2, and you have the setup to find the washer question. Number 31. Same question, so I'm going to just draw it again because I love drawing so much. So now we're going to do semicircle cross sections perpendicular to the x. So now it's going to be semicircles. So to find that volume, a semicircle, the formula for a semicircle is 1/2 pi. We're integrating from 2 to 4. And then the radius, in this case, we need to remember is half the diameter. So this represents the diameter. So half of that would be the radius. So it's half of the curve. And there's the setup for a semicircle, knowing the radius is that, but it's half of that. That's the diameter. (32) For number 32, it says find the average value of that function from 2 to 3. So the average value is an integration question where you integrate from 2 to 3 and you're integrating that function. So I'm going to write that calculus friendly. 4 subtract x to the exponent -4, and then you divide by the difference of the bounds. Now 3 subtract 2 is 1, so when you divide by 1, it doesn't change it. So I would divide by 3 subtract 2, but 3 subtract 2 is 1. So if I divide by 1, same thing. The derivative of the base is -1, so we need a -1 in front to undo it. So we're going to add 1 to the exponent and then divide. And we're integrating from 2 to 3. So the negatives make it a positive 1/3. And then I plug in 3, subtract, plug in 2, and you have your answer. If you wanted to simplify it for fun, 4 take away 3 is 1, and 1 to any exponent is 1. 4 take away 2 is 2, and 2 to the -3, well, 2 times 2 times 2 is 8. So the negative exponent makes it 1/8. So this is 7 over 8. So that would be 7 over 24 if you had to simplify it. The last one? Yes. You got here. A rectangle is inscribed under the curve. I see it. And is bounded by the x-axis shown in the figure below. I see it. Find the point xy that would produce the rectangle having the most area. This is an optimization question to find the maximum. I can get that out. All right. I need a function in terms of x that describes the area of that rectangle. So this rectangle is 1x to the right and 1x to the left. So the base is 2x and the height is y. So a formula for the area of that rectangle would be 2x's times the height, which is the y coordinate. And in the question, it already tells you that the y coordinate is 4 over 1 plus x squared. That's what y equals. Next, I'm going to multiply them together. So that's 8x over 1 plus x squared. To find the maximum value of this, I'm going to take the derivative. So I'm actually going to write it as, well, no, I can just take the derivative using the quotient rule. So that's the bottom times the derivative of the top minus the top times the derivative of the bottom, and then the bottom squared. And I'm going to make it equal to 0. Now, because I do that, I'm only looking at the numerator, because if the numerator is 0, 0 divided by anything is 0. So just the numerator. So that's 8 plus 8x squared minus 16x squared. I'm going to combine like terms and factor. So I have negative 8x squared plus 8. Factor out an 8. I'll factor out negative 8. And now I have my two answers. So positive 1 and negative 1. I'm really only looking at the positive x coordinate, so I don't need the negative. So x equals 1 gives me the answer 0. Make sure that's a maximum. So if I plug in a number less than 1, I need to know that gives me a positive answer, and it does. And if I plug in a number bigger than 1, then this side will end up being larger and you'll get a negative answer. So I need to know it's a maximum. It is. So what point is that? So point, we know x is 1, so that means y is going to be 4 over 1 plus 1 squared. So that's 2. So at the point 1, 2, you have a maximum. And then what is that area? So now use the area formula right here. So it's simple. 2 times 1 times 2. So this point produces a maximum area, and that's the actual area, the maximum area of that triangle. Rectangle. Ha! You're done. Mr. G Math over and out. I'm proud of you that you're doing your work. You finished the assignment. Till next time.